Thanks for the introduction and to the organizers for the opportunity of speaking here. So again, continuing with the theme of complete beginner given a talk to speak to the professionals, I will try to offer also a different perspective on all the formulas and phenomena we see in non-commutative probability, but through the lens of computing with formal power series. And there will be also some algebra symbols. So the main idea is to kind of look at the operations and the identities that appear, for example, moment cumulant relations or expressions for big polynomials and so on, and try to construct a big enough space that kind of encode them in a linear way. So these usually group identities, so we're working in a group of formal power series, and we try to put them in a bigger space where everything becomes sort of linear, and this is more or less the idea of using Hopf. Okay, so before we go into non-commutative probability, let me start with just the most basic case, which is just formal power series, one variable, usual probability. We're not doing anything fancy here. But the point is that we will see how all the structures that I will use later kind of show up already here, and we can, at this stage, there are also only nice tricks that we can do to make some computations more explicit. But then in the end, in the second part, when we look at the non-commutative power series, then they will bring something to the table. Okay, so I start with just a sequence of numbers, M0, M1, which we can think of as formal moments. So again, I'm sorry to the analysts, I'm not worrying about convergence or anything. I'm just taking a sequence of numbers and putting them into a generating series. And here I'm choosing exponential generating series. It's just a choice for me. Right, and I represent them as this formal power series in the parameter T. So what we are looking at really is the ring of formal power series, which I denote here with R, and it has the usual Cauchy product. So this combinatorial factor here is just showing up because I want to write it as like an exponential power series again, so nothing strange. And it's known that just for this easy multiplication, the set of formal power series starting with a 1, so really moment sequences, formal moment sequences, are a group for this product. But then there's the question of computing inverses and so on, and it's not so easy if you stay within the group, right? So there is a recursion one can write for the coefficients of the inverse function and so on. But again, the idea is to try to build some linear operation that represents this inversion in a slightly nicer way. And there are also some other operations that are interesting for us, for example, taking logarithms. So every element in G1 has a logarithm, which is in another set called G0, which is just a formal power series starting with a 0. So these are formal cumulant sequences. And again, I just rewrite the logarithm as another power series with different coefficients, where k0 is equal to 0. And actually, we know an expression for this. It's very classical. This could be by Leonov-Shiryaev, if you want, 59, or maybe even earlier. This is just the Faddy-Bruno formula for the coefficients of a composition of formal power series. And this, we have this polynomial here appearing is the Bell polynomials, which is just counting the number of partitions with certain number of certain sizes. So it has a coefficient in front of a block of size 1 up to blocks of size n minus j. Okay, so this is very classical. And now the idea is to try to reproduce this again with some linear algebra. So here's where Hopf algebras come into play. So we can also encode this moment sequence as just a linear map on polynomials. So here I chose another variable to keep the distinction between kind of what the mu map is eating and the formal variable in the formal power series. I mean, this is just a name. And with this formula here, I can define a linear map on now polynomials, right? So these are just finite series with finite number of non-zero coefficients. And thus we get just an easy linear map, which is sending phi to its generating sequence. So we can think of linear maps as really being a formal version of generating functionals for sequences of numbers. And on this space that I call H from now on, we can put a Hopf algebra structure where the product is a usual polynomial product. So x power n times x power m is x to the power m plus m. And the important part here is that we somehow dualize the Cauchy product into a splitting procedure, as been mentioned many times. So we take the x to the power n, and we sum over all monomials that whose powers add up to n. And we put this combinatorial coefficient, which is coming from the fact that we are using exponential powers. If I didn't choose to put n factorial here, I kind of can move it inside the basis element here, and then all these factorials kind of go into the right places and they disappear. So this is just a choice of basis. Right, so now we have a nice nice space. This is just a vector space with two operations, a product and a coproduct. And as also has been mentioned before, we can put a product here. We can turn its dual space, so H star, into an algebra by using the convolution product, which means I insert a monomial here, I split it according to the previous rule, then I evaluate each map on each factor of the tensor product, then I take the multiplication in the field. This gives me a new linear map, which is just the product of phi m psi. And the theorem here is that the map lambda I defined before, so taking a linear map to the formal power series that it's a generating function, is an algebra isomorphism. I mean, it's just because of the way I define this coproduct, right? So you can see that here, this is exactly the same as here, and it's taking the shifting of the coefficients here going into the powers. Okay, so nothing fancy here. But the point is that then we can try to, for example, compute inverses for this product now, which is now happening in a linear space. So there's no more no linearity coming from a group, more or less. And then, so moment sequences are then identified with just maps sending 1 to 1, so the units, so the constant 1 to the constant 1 in the field. And this is also a group with unit the projection onto the scalar, so I just take the constant coefficient of each polynomial, and the inverse is given by the Neumann series. Yeah. So this is the usual way of inverting linear map using a power series. And this is still not good enough because it involves taking powers. So it's still kind of a nonlinear operation. Right? I need to compute these powers, which in this case, since given the easy formula for the coproduct, I can. So what does it mean taking the jth power here? This just means iterating the coproduct j times, which means splitting the monomial x to the n not only in 2 parts, but in exactly j parts, whose powers add up to the power I had at the beginning, in this case n, which you can see it's what's expressed here in the sum. I get this multinomial coefficient now from the same formula as before, and I get this minus 1 to the j from this minus sign. And maybe you will recognize that this is the formula just for the multiplicative inverse of a power series. But somehow we reproduce it now using this, again, linear structure. And we can also define a logarithm that takes a linear map sending 1 to 1 and gives me a linear map sending 1 to 0 by the usual power series, but now the powers are replaced by convolution powers. Okay, so I've not done nothing else than just rewriting what we know already for power series in a slightly more complicated way. But the nice thing is that now we can try to leverage some of the structure that Hopf algebra is bringing into the picture to try to get either nicer relations or more explicit formulas for some of the identities. Or maybe even, again, try to get away from this nonlinear taking powers and try to make everything just live in a bigger space. So as was mentioned before, so we have the character group, which are just algebra morphisms from H to K, so are linear maps, not only sending 1 to 1, but also respecting polynomial multiplication. And the nice thing is that this is also a group, it's a subgroup of the group I mentioned before, but here inverses are given by just a single linear composition with a single linear map that's called the antipole. That it's, in general, the solution to this equation here, which for a general Hopf algebra, it's maybe not explicit, but in this case, it's very easy. It's just this. But there is one problem. This is kind of too simple, right? Because if we're thinking of moments, The map mu being a character, meaning respecting polynomial multiplication, means that I have an independent random variable that's independent to itself. So every moment splits as a product of moments. This can only happen when I have a constant random variable, which means mu of x to the n will be just mu of x to the n. And then this means that through lambda, through the generating series, it would be mapped to e to the tx, or t to the m1, right? With just powers of the first moment. And this is the other instance of the Marcinkiewicz theorem that was mentioned at some point. So have either Gaussian or constant. These are the only two generating series that can be with finite number of cumulants. And then it makes sense that the antipode is this, because the inverse of this map here would just be e to the minus t1, which is exactly doing this. But we want to be able to express kind of arbitrary moment sequences in a similar way. So what we can do is just say, okay, I could just go to a bigger space, which I have here, which is just taking the symmetric algebra over my polynomials. So these are, so to speak, polynomials of polynomials. And to just not confuse, to get confused with the usual product, I will put a bar. And this is similar to what Joachim was talking about. So I just not take single polynomials, but I take sequences of polynomials, and I don't care about the order. Right, and as I wrote down here, I will put this part to just not be confused that this is not a symmetric usual product of polynomial, but this is an abstract product that I'm just adding to the picture. And in this case, this kind of frees me from the burden of just having multiplicative maps being just representing moment sequences of constant random variables, but now I can represent everything, because I can always lift mu that it's living here, that it's in this g of h. It always lifts uniquely to a mu hat, let's say, that it's a character on h hat, right? Because I just declare it to be multiplicative, but with respect to this extra product that I added here. And in that case, I can formulate the inverse here in terms of this antipode, which is, again, the formula that we saw before, but this is now internal to h hat. So it doesn't require knowledge of phi or anything. This is just map that I compute once, and I can use it for to invert any linear map. And then again, we have logarithms and exponentials, and these will express moment cumulant relations for classical moments and cumulants. And so the theorem is that by doing this extension, I actually didn't lose anything. So restricting characters, so maps multiplicative with respect to this bar, to just maps on polynomials without the bars, just sending one to one, is a group isomorphism, so I represent the same operation. But now I can just compute in H and apply the map mu at the very end. So basically the formulas that we usually get, for example, moment cumulants, really don't depend on any information about what the moments are. It's just a combinatorial formula in this Hopf. And then we can also apply this to get, for example, formulas to weak polynomials that are defined by this generating function. So what we are doing here is just saying my coefficients of the generating functions are not just numbers, but they can also be polynomials in some other extra variable. They can play the same game. And the statement here is that this still works. And what we get in the end is by using the same Hopf algebra, so where we know how to do calculations, in particular, we know how to invert this map, we can get an algebraic expression for the polynomials that appear here in this generating function by just using the same coproduct that we know from before and the same inversion formula with this. And this also easily generalizes to the multivariate case, right? By just changing the coproduct by taking care of now multinomials, if you want, in several variables by a similar formula, and then we use the exact same map, and we can get also multivariate weak polynomials in the same way. So they are always expressed by the same map. Whereas if we try to work directly with the power series, this becomes a little bit complicated. Okay, so this is somehow the ingredients we have. So we have some identities between generating functions, and we built a big Hopf algebra that somehow encodes them through the coproduct and the antipode. Now we try to do the same for generating series of the generating series that appear in non-commutative probability. So again, just to set some notation, we look now at non-commutative power series. So here I'm slightly generalizing what I said before. So the scalars are not only a field, but they can be an algebra over some field. So just to allow for having polynomials of coefficients or some other extra thing you could want to put there, but it doesn't really matter. The only thing that matters is that they commute with the x variables. But other than that, I don't have any restriction on what this can be. And a generic element, I write it as a power series, right? In this non-commuting variables x. So we have some coefficient. Have some coefficient here in front of the monomial xi1, xik, and just to make the notation a little bit nicer, I will use word notation. So this monomial here will be represented by the word I1 up to ik, word on the integers. So this is what this star here is representing. So this is just a clinic closure, words on integers. For example, when I write 11, this I don't mean 11, but I mean the word 1, 1. And we have two distinguished sets, again, corresponding to formal moments and formal cumulants. Now they are in non-commuting variables, representing the fact that I want a different coefficient from the moment of, say, B1 and B2. It's different from the moment in general, from the moment of B2 and B1. And this is encoded through the non-commutative here in the variables. Okay, so there is one operation that appears, we've seen before, which is called a shifted composition. So this is kind of the operation between power series that's underlying the moment cumulant formulas that appear between, for example, free cumulants or Boolean cumulants, and also monotone cumulants and so on. So again, when I have two formal power series starting with a 1, I can define the following bullet operation, which means multiplying f by g, but I replace the variables in f by a shifted version of the original variables by the power series g. And for this, I require that g starts with a 1, which is written here, so that my new variables are sort of a perturbation of the original variables. Right? I don't want coefficients appearing here or the variable xi, the linear part disappearing or something like this. So really, I want just a perturbation of the xi by the coefficients of g, and this could mean that the perturbation is really just higher order monomials in the variables, in the same variables. And just for notation here, when I write xg of a word, I really mean multiplying these new variables in the same way as before. So I put x1, then I put the full series g, then the second original x variable, then the full series g, and so on and so forth. And then when I just have one variable, this just reduces to a usual composition of power series, which is what we would see in the classical Okay, so now the game is try to build again a big enough Hopf algebra that can help me represent this operation and hopefully get some statements about moment cumulant relations in some nice way. So now again I take as V the linear span of words. So these are play the analogous role to the monomials x to the power n that I had before. So these are the indexing set of my coefficients in the power series. And then I extend this to a further tensor algebra. So I take words, and then I take words of those words. So this is in complete analogy to what I did before, to be able to kind of extend everything multiplicatively and be able to leverage the antipode and so on. So, which means in the end that this space H here is spanned by what I chose to call sentences, which is really just words of words. So each letter here is actually a word in the original alphabet. And we can define this coproduct that was introduced by Kurush and Frederic over 10 years ago, which works in the following way. So I take a word and I pick a subset of the indices, and I extract them. And in the places where I extracted a letter, I just put a bar. So this is not exactly the same as you would expect. Like it's not just extracting and putting the leftover monomial on the right, as we had before in the commutative case, but here I somehow want to keep track of where I extracted each variable, because there's an order I have to keep. And just to give you an idea, an example here with 3 letters, I can extract the empty set. I can extract the set 1. Here I put the variable 1 and the leftover part here. But when I extract the variable 2, since this was in the middle between 1 and 3, I just choose to put a bar to remember that I extracted something from there. Since I'm always extracting just single variables, there is no confusion here because I can only put one single thing there. And the rest continues by extracting y3 or the subset 1, 2, 1, 3, and 2, 3, or the whole set 1, 2, 3. One important thing to keep in mind here is that I always keep the product on both sides in the original order. Here I extract 1, 2, although it's a set, I always remember that there was an order 1 and 2. So on the left, I have to put 1, 2, and not 2, 1. But other than that, I hope it's fairly clear what this coproduct is doing. And again, the end result of this trick is that if I define the same map, so mapping a linear map on words now, to its generating series in the same way, then I get another group isomorphism between convolution product for this coproduct and the shifted composition of formal power series for non-commuting. But in this case, since we have all this extra structure going around, there is a little bit more that we can say. And because in this case, which is not the case for the commutative side, this coproduct splits into 2 parts, where I split the sum over all extractions, where I keep track of whether the first letter is on the left-hand side or the right-hand side. And this is what this arrow here, this symbol here is supposed to mean. So when it's pointing to the left, it means that the letter 1 always appears on the left of the tensor. And when it's pointing to the right, it means that it never appears on the left, or always on the right. So obviously, when I sum the 2, I obtain the original coproduct. So these are the only 2 possibilities by fixing the letter 1. And this gives me a little bit more than just a bialgebra, but it gives me what's known as a non-shuffle bialgebra, meaning that since this is the sum and this sum has to be co-associative, there has to be some relation between these 2 coproducts. I will not write it down, but this allows me to say a little bit more. So in turn, when I just dualize everything, I can split the original convolution product into 2 different half shuffles. So I get the original shifted composition split into 2 sub-operations, so into 2 actions of functions into each other. When translated again to generating functions, means that I just split the full action, so the full shifted composition, into just a simple composition without the shift with G outside, or I put the G outside and I have to subtract the constant term. Obviously, when I sum the 2, I just get the original bullet operation, but somehow these are the 2 operations that will appear later for Boolean and free cumulants. So they are both kind of the 2 sides of this full shifted composition that I defined at the beginning. Maybe since I'm running out of time, let me just skip to the link with non-commutative probability. So now we take a non-commutative probability space B, and with a state, which is this curly phi, and some set of non-commuting random variables on B, and I define the obvious map. As I said before, I just take phi of a word to be the state phi evaluated in this order product of the variables bi1 up to bin. And since H now is the tensor algebra over V, I can just extend it multiplicatively without requiring that the variables are independent or in any way. Right? So this combinatorial device allows me to get somehow multiplicative maps for even though the variables themselves don't satisfy any kind of splitting of this expression. And then it was discovered by Kurosh and Frederic that I can actually find two. I can define two further linear maps here, beta and kappa, that are representing the free and Boolean cumulants by making use of these half shuffle structures that appear before. So in total, the expression for the solution of this equation here, kappa and beta, are given by these two relations through the moments. And you will recognize this as the equations defining the free and Boolean moments. And the reason for this, maybe if I have 1 minute, is that when I do kappa, this half shuffle kappa, let's say I have I1, I2, I3, I4, I would have by definition kappa tensor kappa, and I would have to extract subsets of this word and put some on the left and then some bars on the right. But here kappa has this property that whenever it sees a bar, it vanishes, right, because it's somehow a logarithm. And we'll see that what I get in the end, for example, when I extract I3, let's say I2, I4, I had I1, but then I have to put a bar here. 1, 3. And then 2 bar 4, right. And this would be one of the terms. This would really correspond to, this would be mapped to kappa I1, I3, kappa I2 bar I4. But since kappa vanishes on bar products, this will be 0, and this would be corresponding to the partition 1, 3, 2, 4 that I don't want to see in my expression. And the same, and for the same reason, when I do the computation with beta, since it uses a different one, which means that 1 should never appear on the right whenever it is a bar, means that I always have to keep a full interval having 1, 2, 3, because I don't want bars on the right, and this will give me the sum over interval partition. Okay, so now mapping this to the generating functions means that between the generating series, I get the following two relations, so I can express the moment generating series through this equation that features this insertion map. So this was the left half shuffle operation, the splitting of the full shifted composition. And for the Boolean, I get just simple multiplication on the left. And these are basically we obtain by knowledge of somehow these fixed point equations at the level of the Hopf. Right. And then we have a similar statement for the monotone cumulants, but this becomes a little bit more complicated because I have to use the full composition. But in the end, just quickly saying that this is the part I skipped, but for the sake of time, let me just say that this somehow also allows to obtain the 3 factorial coefficients that appear in the moment cumulant relation for monotone cumulants from an additional structure that appears through these half shuffles, which is known as a Prilly algebra. And this has to do with rooted trees. So in the end, we can also give, let's say, a different point of view on the 3 factorials that appear for monotone cumulants through the use of this Hopf algebra structure. Okay, that's all I wanted to say.